All good? Yeah? Should we start? All right. So how's everyone doing? Good? Okay. Does anyone remember what we talked about last week? Yes? Okay. All right. Did anyone do the case study? Some? Yes? No? Maybe? Pick one. Which one have you picked up? If anyone wants to give the example of which one did you pick up? Not yet? Okay. All right. Make sure that you do, because I'm not sure, but how maybe Professor Saw might want to basically have a look at two of them and have them present here, if anyone has interest in it, right? Okay? All right. I'll have one more case study, which is more related to the hopefully Indian environment. So we'll see that. We'll probably introduce it tomorrow, and then we'll see how exactly it goes with that. Any questions from what we did last week? Yes, no, maybe it's an opportunity to say that I didn't get anything. Start all over again. Maybe we'll do that, but I'm not sure. All right, no questions? Then let's just continue. What we're going to do today is that a little bit that was left from last week, which was more about the attention and the transformer. Two things that you should probably know if you kind of claim that we did something about generative AI or large language models. So got to know something about it. I have shifted focus from last 2 days or so, if you notice about it. All I wanted to do most is that you get the intuition of what's going on inside those systems, not necessarily all the calculus or all the mathematics that go behind it, right? So very quickly, if you remember that, this is what we have been talking about all along. Now, I've put a lot of these diagrams here. You will see them in the next hour or so, one at a time, and then try to figure out what exactly is going on. Basically, two things are clear, that they're not the databases. So it's not that you're asking a question and a system is running through their database and then trying to find the right match or the right answer. They're not. They are a model. That's why we call them as model, right? We're not calling them as systems per se, but they're a model which is trying to put together words in some shape or form, right? So if you look at it, I said something about functions. We talked about surfaces. We talked about the neural networks, and we talked about a latent space, right? These are how words are organized roughly. So we're going to look into all of these things one more time, this time from the perspective of transformer and attention, right? Has anyone heard the term attention before in the context of large language models? No? Okay. All right. So let's try to understand why we need that concept, right? And as again I'm saying that, let's just try to get an intuition of what exactly we're doing. Now, clearly what we have understood after the week one, that every time we're running the model, it's trying to predict the next most probable word that will fit into a sentence. So if, let's say, it has seen the best thing about AI is its ability to. Now, how does it predict the next word? Now, there could be a possibility that the best thing about its ability to learn, predict, make, understand, do, like a lot of common questions are possible, right? So there is no right or wrong answer. So that's number one. That's where we moved from sigmoid to softmax, if you remember that. What we need to do here, or what the system or what the model does, is that it tries to figure out what are the most probable answer, and it assigns them probability. Right? So if you look at this example, and I'm not saying that these are the only words it will pick up or these are the only kind of probabilities it will get, which word is more likely to be picked by the model? Come on, have a look at it. We have the choices and we have the probabilities. Learn. Anyone who disagrees or wants to say something different? Yes, if we are picking up the highest probability one, then obviously it will pick learn, but we know that we can actually tweak it by having those parameters top P, top K, because if it is always picking the highest probability, there's not going to be any variation. You will always get the same response. Right? This is what we talked about last week. So, and then it keeps on doing this in the sense that every time it picks a word, then it looks at the whatever the sentence it has so far and then says what's going to be the next word. So let's say it did not pick the learn. Let's say it picked the create, which is not even here. So you say create words that are both exciting and so forth. Continues, right? That's a very simple way the generative AI is functioning and or predicting every new word that it is coming along. That's clear, right? No confusion on that. So let's just continue to see. If we are changing, then you can see that if it picks learn, it might go in a different route. If it picks the ability to really, it can go in a different sentence altogether, examine. That's where you see that, because we do not want it to be predictive all the time, in the sense that you know that if I give it this prompt, this answer will come. And that's where it has, in a way, if you think about a little bit of a conflict also. Because if you're giving it a prompt, the Kumbh is in 2025 is happening at Prayagraj. You don't want the randomness to say that one time it says Prayagraj, next time it says Ujjain, then Haridwar. So in some cases you do want it to give predictable, correct answers. In some cases you want it to be a little bit random. That randomness is two sources. One obviously is your tuning parameters, because you're telling it how random you want the answer or how definitive you want the answer. And the second thing is this, for it to understand how best it understands the meaning of the words, right? The meaning of the words are important, and that's where the attention will come in. Okay? So if you look about it, this is a kind of graph that's coming in terms of what exactly are the possible words it's looking at, and then trying to figure out which one to pick. Now, where do these probabilities come from? You saw these probabilities here, right? 4.5%, 3.5%. Does someone remember where these probabilities are coming from? We looked at the bare minimum or a simple example. But where do these probabilities come from? Any idea? Come on. Sorry? Yes, but what's the input to that function? Alright, so what did we say? We said that all these models learn, that learning leads to weights and biases. Those weights and biases are fed into a function. In this case, it will be softmax. So then what happens is that based on the weights and biases, and we looked into it, that these weights and biases follow a special equation, and then they are being summed up, and those summed up values are sent to the softmax, and then if there are 10 different potential choices, the probabilities are calculated, yes, based on the base probability, right? That's where these probabilities are coming from. Just keep that in mind, where these probabilities are coming from. So when you have started with the very first word, the, right? Lot of options exist. That those probabilities start from very beginning based on like what you have seen. So it will go back in its history and say, if I see the first word as the, what would be the next possible word? And keep in mind, it may choose the totally wrong word. It may choose a word that you did not intend it to be chosen. How do you kind of tell the model to choose what you wanted to choose? Prompt engineering. That's what you're telling the model, because the model doesn't know what you intend it to do. Your intent is conveyed to the model using the prompt that you're providing. Now, all of you have access to, let's say, same model, right? ChatGPT. How well your prompt is will determine how well the model responds to your prompt. Right? All right. So that's what you show your intent to the model, but the model still has to have some probabilities to begin with. Those probabilities are coming from the learning. Now, think about it. We said that they are learning a word at a time, but what if the model is learning one letter at a time? So not the word the, but really the first letter T, then H, then E. Is that going to be better, or is that going to be not so good? What do you think? Why? Why? I mean, I agree. The answer is correct, but then why? We should always ask.
More complex
More complex?
for the model to predict.
Okay. So, yes, to some extent. So, what we're going to say that here, not all combinations of the letters are the correct acceptable words in English, right? So, THE is a word that has a meaning, but TEH is not. In a way, there's no semantics attached to that. So, yes, you can start with one letter at a time, but it increases the size of the learning space. And then majority of that space will consist of letters or words or combination of letters which are not having any meaning or meaningful semantics attached to that. Having said that, we're going to use the example here again for intuition, how the model is learning. Okay, so on the or your left hand side, you see the distribution of each individual alphabet in the English language text, which, let's say, some model has seen as part of its learning. Does that make sense? Which specific alphabet has the highest occurrence in a typical English language text?
E.
That's based on your understanding, or you're looking at the graph?
Looking at the graph.
All right. What's the second one? Right? Okay. So, intuitively, do you think that kind of sounds right? Or somebody might want to disagree with it? So, the J, the Q, and Z are the ones which you don't find very common. E is common, A is common, R, S, T are pretty common, M and N are pretty common. G, H are common. So if you look at the language, the words that you use, you would see that that's the distribution, right? So my point here is that if you're trying to predict the next word in the same probability, IID, if you remember, the same distribution function, that's the distribution function if you're using one alphabet or trying to pick the next alphabet, right? That's what it is. How many of you have played Hangman? Hangman is a game, right? How do you predict the next character or word? You pick a character at a time, right? How do you pick it? Come on, there were only one or two hands going up. Do you know Hangman is a game? No? Oh. All right, so let's play the Hangman now. So Hangman is like you are given a word, you predict an alphabet at a time and try to predict the word.
We know this game.
Huh?
We know this game, but doesn't know.
The name of the game, basically?
Yes.
All right, fine. So who can predict this word? Now, again, there are multiple words like this, but you predict first alphabet and I'll tell you what it is and then we go on that.
A.
Sorry? A. A goes here. So one wrong.
Is it a question of permutation and combination?
It is, but the game is a game. Let's just try to predict.
E. P.
One at a time. Which one? Who said P?
P.
P. Okay. All right. What was it? E. Okay. Now I'm going to ask, I'll stop it here and then I'm going to ask the question, why did you pick A? Who picked A? T? T comes here. Okay. But why did you pick A first? Who's going to give the answer? Like, yeah.
The word is going to have vowels mandatorily, so I started
With a vowel, A, E. Yeah, but see, you have the distribution right there. So you should have gone with E first.
and that's why I said E only.
Okay, right. All right. Why P? Who picked P? Okay. All right. And then the whole idea is that if you are picking one character at a time, you should pick going by this distribution because that's the most likely distribution. Having said that, once you have figured out one or two, now you are not picking the individual base probability comments because now you already know it's EEP. Now what it could be? Which one? No, you are picking one alphabet at a time.
S.
Okay, one. Okay, which one should I take? S. Okay, let me write the H here first. S here. Okay, T is already gone out here. Yes. Okay, that was the word I have. Okay, the point I'm trying to make here, if you think about it, when you are picking the first one, you should go by that distribution because that's the most common distribution. The moment you've got one character, one position right, it's no longer that one. It's that plus something else. That's the base probability. Given I have already fifth character as P, what would be the fourth one or third one or second one or the first one? Right? If you look at this one, can anyone guess what this is showing? Correct. Now, darker is the color, more likelihood that that combination is going to appear. So if you look at this, this says that a combination of Z and W coming together is a very low likelihood. On the other hand, if you see this, A and M, A and N, A and P, AR, AS, AT have a very high likelihood of occurring together. Is that point clear? Now I can't show you three dimensions, it's just become more and more difficult. But if you think about it, if you start from looking at the probabilities of a single alphabet, two of them together, three of them together, four of them together, you're looking at a probability distribution function, something that we talked about a lot last week, right? Where do these things come from? Learning. As you are sending learning input to the model, it is figuring out that, okay, I saw 13E in 100 characters that I've seen, or 300 in the 3000 that I've seen, or 5 million in 10 billion that I've seen, whatever the number. It's calculating the probability every time. One tuple, two tuple, n tuple, things like that. So keep in mind, all that is going on here is trying to figure out the probabilities. That's all it's going on. If you learn that, you will be very, very successful on this game as well, right? Try to figure out. Now, why we are not doing one word at a time? A, because that probability is not sufficient, because we are trying to kind of depict higher level constructs. Second thing is that, as I mentioned earlier, not every two alphabet combinations are the valid words. Can it still produce meaningful sentences? Yes, it can, but it's going to take longer. So here is an example. It's trying to predict random words with increasingly going by 2 grams, n gram. Now, n gram basically means that the combination that you're doing. 2 grams means the two words together. So this is an experiment that started with random words being created with 2 alphabets or 3 alphabets at a time. Makes no sense. You keep going on multiple iterations, then in the 5th iteration it started forming words which had some meaning in English. So the point here is that if you're trying to generate sentences, it may not be worthwhile starting from a single character as a unit. It's better to go with a larger character. Now look at the other side. If you tell the model that treat every word like a 5-character word, is that a good thing? Right? Even that is not a good thing, because if you say 5, this has every word which is more than 5, right? But it missed out on was. It missed out on high. I mean, I'm just not saying that it did, but it won't, because if you tell it that every word will be 5-character, it will miss out ale, for example. It will say that that's not complete, that's incomplete. So what people realized, or researchers realized, that we don't want 1 character as a starting point. We don't want to give it like a 5-character that you have to form a 5-character. Let the model figure out what's the best size, or which is the best word to keep it. Say, for example, it might decide that, where did the high go? Yeah, high is occurring enough number of times so that it deserves to be counted as something important. OIA probably is not occurring as many times as whatever warrants special attention, so it need not be what we are interested in. So really what is going on here in modern models is that we are not telling them either pick 1 character at a time or pick at least 5. Let them discover based on their own learning that what's the most appropriate size of, now let me introduce a new word, token. So we're not calling it a character, we're not calling it a word, we call it as token. The size of the token is not predetermined, it is discovered by the model as it's learning whatever is the underlying text is. Make sense so far? All right. So what is a model? That's what the model is. It estimates probability by which a certain token or sequence of characters will occur in its training data. Yeah? Now, because we are not telling it to use a token size of 1 or 5, what was discovered, this was not intuitive, that it is actually creating the token which were never part of the input data. That's part of its learning. So for example, for whatever it's worth, and I'm not saying that's the one, it may be picking this as a token of interest. I'm just giving an example. So when people started looking at the model or the internals of the model saying that which token it found interesting, they noticed that, and which is what we were saying here, not this one, too far, yeah, that some of those tokens were not something which were explicitly part of the input data which was used for training, which means the model is trying to say that, or figuring out that, not just the words that you're providing me, I find some more combination or some more sequences of alphabets which are of interest, and I'm using those as tokens as well. Does that make sense? Yeah? All of these are models. We have seen a couple of these examples. That is the original observation on the top, your left corner here. There are multiple functions that are trying to approximate the occurrence of these observations, which is really a model. Now, you have 3 different functions trying to approximate the observed phenomena, and each of these lead to a model. Right? So, let me ask another question. Same question we have asked a couple of times. I asked this morning also. What is the model trying to learn? I mean, one way we mentioned, and then we talked about weights and biases, but let's try to give a slightly higher level definition. The model is trying to learn which function should I use to predict the next token. So, at least for today's lecture, let's use the word token, because we will use that in the context of the LLMs. So, learning for the model is basically trying to find the right function that approximate the distribution that has been observed. All the words you should know very clearly: observation, distribution, function, all know that, right? Okay. So, couple of things that we did earlier before we get to the transformer and the attention. We saw the example of a single perceptron or a neuron, how that functions. We also determined that single neuron can only approximate a linear function, i.e. it can only do AND and OR, but not the exclusive OR. But if we introduce a hidden layer, or the layer in the middle of input and output, then we can have it learn the nonlinear functions as well. So one of the experiment that was done was to say that what would it take for a neural network to discover this function? Anybody here who's electrical, electronics, or telecommunications? Do you recognize this function? Okay. Sorry? Sorry, say it again. Yes, digital signal, but what would you call that function? Sorry? It's a step function. It's some kind of a step function, right? Now, the idea was that we don't know the amplitude frequency. We can make a determination of it, but it's a step function. Let's say that. Can a neural network learn that function? What do you guys think? I mean, obviously, the answer is yes, because we have come this far. But as the research was starting, we wanted a single input and a single output, and we wanted to see that can we create a neural network that can learn this function. Not that you tell it, you can tell it because we know this is a fairly standard function. Anybody who's doing the, I guess, first year electronics will come across this kind of a function anywhere. The issue was that, can we make a neural network that will learn this function by just giving it inputs, not telling it? So, can anyone guess what would have happened, or what would be required to do that? So this is the kind of experiment. So if you go by this, so this was the structure that we started with. It was very clear that it would not be one neuron that can do it. Researchers started with two different layers here, two hidden layers basically, and single output. So one thing is clear: single input this way, single output, which means that it's a sigmoid function at the end. 4 neurons in the first hidden layer and 3 in the next hidden layer. Now, one may argue or ask the question, why 4 and 3? Why not 2 and 3? Or why not 5 and 3? That's something which, as I already mentioned, that's kind of research. So here's what was observed. The same structure of the neural network. After 10,000 examples, this is the function that was learned. After 100,000 examples, this was the function that it learned. After about 1 million examples, this is the function, and about 10 million examples, it got the function right. Same neural network. It's just changing the weights and biases to get to the point where it learns the function that we want it to learn. What does it tell you? I mean, is it good? Is it not so good? Or what do you think is going on? So one thing is clear. That's how the research is done. Painstaking, one step at a time, one neuron at a time. You got to repeat it 10 million times. I mean, okay, you don't do it manually. You were writing programs to do it. And those things become the building blocks, right? In the sense that you realize that. So if we go from that example, this is what it was learned, in the sense that single sigmoid, that's the function it learns. That's the linear function. That's the only thing that a single sigmoid can do. You introduce 2 lanes in the hidden, it learns this kind of a function. You have 3 in one hidden layer, it learns this kind of a function. So all of it was learned by the researchers one step at a time. You have this kind of neural network, you do this. To learn this, you need this structure. So you think of it, these are as building blocks. So this was the first section I wanted to cover, in the sense here what the learning is, and then we talked about last week a single neuron and then basically only thing we said that you need a hidden layer if you want to do a nonlinear function. Now you see that how these things were building one neuron, one layer at a time, and then you start learning more and more complex functions. That's what basically it is, right? Okay. Any questions in terms of figuring out, understanding what we did? The two concepts, if you think that we learned right now, one is the new thing I introduced called token, which we talk about a lot more. And then the second thing is the intuition of n-gram, in the sense that what's the probability distribution if it is 1 character, 2, 3, up to n. And then I said that we are not telling model what should be the size of the token or the words. We said it will learn on its own. And then we saw some examples of how the neural networks learn more and more complex functions. Any questions? Yes, no, maybe? If you have access to any programming network, if you want to make sure that how the neural networks function, just try doing these kind of experiments and then see how exactly. Theoretically speaking, if any of your electronics lab can be simulated using a neural network. Pass on the inputs and outputs, and then you let the models learn. Any questions? Okay. If not, let's move on to the next topic. How do we take these tokens and see that they are used in LLM? So let me, or the neural network. So let me introduce another word called embeddings. I used it last week, last day, in terms of defining what these embeddings are, right? So what have we understood so far? That when the learning data is provided to a model, it converts the incoming data into tokens. These tokens are not necessarily words and have no fixed size either. What was observed, and I mentioned this on the earlier slide, that it was forming the tokens with the combination of words or combination of the alphabets which were not even necessarily in the input data. Okay. Now, all these tokens, and if you remember that very first diagrams I showed, is kind of a word cloud, will end up into some kind of a space. We talked about the space saying that it's a higher dimensional space than we can characterize. But in general, if you think about it, what an embedding is that it is trying to capture or trying to absorb the essence or the meaning of the underlying domain represented by numbers. So this is another key insight that you get here. Even though these large language models or generative AI is dealing with the words, text, and images, or whatever the case may be, we have seen the 3 examples I gave you in the case study. One was audio, one was images, the one was protein data, and those kind of things like health related. Under the cover or behind the scene, it does not understand. It doesn't know what protein is. It doesn't know, or at least that's what we think. But it is converting whatever the meaning is in a combination of numbers. And numbers not necessarily in 2 dimensions, but in a very high dimension numbers. And what researchers are finding that even though the model doesn't understand what do we mean by mango or papaya or banana, but when you look into its space, these tokens, because for it they are token, all the fruits are together. No one is telling it that mango is a fruit, apple is a fruit, banana is a fruit, and they are related. All it's seeing is these alphabets. It's converting them into string of numbers in some very high dimension. So the concept of embedding is taking a word or a token and assigning it as a sequence of number in a very high dimensional space so that related concept come together. Nearby things are represented by nearby numbers. Now, this is the beauty of this model that people discover. no one is telling it that alligator and crocodile are related. It doesn't even know that the alligator is some kind of a reptile animal. Still, it's able to figure out that alligator and crocodile are together, and the chimpanzee belongs here, not here. The elephant is in a different kind of a domain. So it's figuring out. All of it is happening by figuring out the right embedding, which is assigning some set of numbers to each token which it finds of interest. Now, this is an example. If you look at the real embeddings, you may not see, okay, I shouldn't say you may not see, you will see these words, but you may see some other tokens also which the model thought they were of interest. Okay? Now, some people started thinking it's sentient because it's learning which no one told it. No one told it. No one told it that papaya and banana and melon are related, but it discovered them. It found it out. Okay? Embeddings. What we do, one other thing, if someone remembers from last week, I mentioned that if you want to go beyond the prompt engineering, the next kind of activity that you can do is retrieval augmented generation, RAG. When you are interacting at the RAG as an application in a RAG, what you're doing is that you're short-circuiting the learning process and then embedding the words at this space, at this level. So basically, you're trying to influence model by going one level deeper. Okay? So now let's focus a little bit more on the concept of embeddings, or what we call embeddings. Okay? So how do these things look like? Very difficult to visualize because it's a very high dimensional space that we are talking about. Some examples here. Embedding vectors look like this. The cat looks like that one, dog, chair. So for a human, for our understanding, because we can't visualize vectors in higher dimensions, it's very difficult for us to make any sense of what is going on in there. That might be how our brain perceives the cat or a chair as well, right? We don't know that. But that's how we know that, because this is nothing but a computer program, and it's holding some data inside, so we can figure out that this is how it looks like. This is how a chair looks like in one version of a large language model based on whatever learning it did. Make sense so far? Okay. Now let me say one more thing which might be quite unintuitive. So this is meaningful, right? Because we can make sense that there would be an embedding or a token for apricot, peach, cherry, pineapple, fig, whatever the case may be. But don't just go by that. For the LLM, every one of these things is also an embedding. This could be temporary, but at the end of the day, if it's predicting the next character, next word for each of these sentences, they are also assigned a vector or assigned the values or numbers that will make them as another embedding. Is that point clear? So if it's predicting or trying to predict where do the probabilities come from, it will learn that where is a token, then it will learn that where do is a token or an embedding, because that's where it tries to find out what is the closest to this in whatever space it has. So these embeddings will continue to grow and will have every intermediate sentence as part of these embeddings as well. That's what my point here was. Okay, so what goes on is that any sequence of token that is, let's say, seen so far will become an embedding, or it will try to find, do I have this already as an embedding in my space? Okay, so think of it now, what I'm saying here. I started half an hour ago, 40 minutes ago, by saying that it is not a facts database. It is not. But everything else is an embedding. So it may not be doing the exact search. Somebody asked last week a question about fuzzy search. In a way, it's saying that, do I have this as an embedding in my space? If not, what's the nearby word, term, token that I have? So there is always a search involved. So literally what's going on is that whatever the tokens you've seen corresponding to the text which is coming input in your prompt, say for example, try to find an embedding that represents those. If it already has it, great. If it's not, let's try to find, either create a new one or try to find the most semantically meaningful next to it. That's all it is doing it. Does that make sense? Okay. If you're using a ChatGPT, there is a context size or a window that says 8K. Anyone remember that? Right? GPT-2 had a much smaller window, 3 had a larger window. What's the significance of that? Any idea? Yeah? Anyone? So two things actually. That's the context window. So one thing it's saying is that you can give it a token or a set of tokens which can go this far, and it will consider them to predict the next one. The other way, it says that theoretically it can have a space which has 8,000 dimensions. We haven't seen in the current LLMs that it goes this far. There are examples of up to 2,000 dimensions that it is constructing its embedding. Now what it means that it's not going up to 8,000, it is finding an embedding within the 2,000 dimensions that it either matches with or creates a new one. All right? Fair enough. So that's what it does, and then try to figure out into a new embedding, generates an array from about 50,000 values, which is what every time it thinks that it's producing it. Okay, all right. The same pipeline being implemented multiple times. Nothing is explicitly engineered. Everything is learned from the training data, right? We are all very clear. Let's look at an example or another example of the embedding space here. So, not only the model figures out the positioning of these concepts, it also notices that some things move together. Plaintiff, defendant, trial. Not only it finds that the plaintiff and defendant are close to each other, they are also linked to a trial in some way, shape, or form. Now, these are all observations that once the model has its embedding, then the researchers are trying to figure out is that how is it doing what it is doing and how is it doing so good. Similarly, it's trying to find out is that, say for example, street and road are very clear. State and property are close to each other. Growth and economy are, science and degree is added together. So a lot of things that it is learning is trying to figure out where exactly they belong, and are there any what is called as semantic laws of motion, which is what it's saying is that if you change a plaintiff, maybe the defendant and the trial will also change. So these tokens, these concepts move together. Okay, this is also a learning that is happening. That semantic law of motion also tells in the sense that how do you create an adjective for a noun or an adverb or a pronoun. So it's also learning that you have on the one side the one tense, on the other side is interpreted, agreed, recognized, authorized, and they're all appearing together. On this side, if you see the adverbs all appearing together, you come this side, the nouns appearing together. So not only it's learning the embedding, but it's also learning the grammar without anyone telling it and organizing it correctly. So that's also something what this model is doing. Example that we had seen last week, but now in the view what I'm defining as meaning space and semantic laws of motions. it's also figuring out is that the relationship between I and C is what ear and hear is. Green to go and red to stop. It's also learning that. We saw the example of this one. Men, women is king and queen. It's also figuring out there's a circle between plant, bird, egg, seed. They are relative to each other. All of these kind of things it's learning on its own. And what we are it's emerging a field called meaning space and semantic laws of motion, where the embedded token in a meaning space or a vector space are moving together. Make sense? How many of you are frightened now? The machines are someday becoming so important that they will take over the world. It's learning a lot of things. It's learning a lot of things very fast. Right? Any of you have heard this? I'm writing it, don't ask me to. It's one of the exam, USMLE. I think it's called US Medical, I'm forgetting L, but E is exam. Okay. Not sure. What's the entrance exam for medical here? In my days, it used to call PMT or CPMT. NEET. Okay. So USMLE is an exam basically that someone has to, it's kind of an entrance exam to get into an MBBS equivalent degree. Okay. Most of these models actually can write USMLE exam and pass it. So they have gone to that extent that they can write an exam and get enough ranking to get an admission. So it can do the USMLE exam today. All right. So pretty soon you will be fighting against an agent which is coming as a LLM. Probably doing a lot better than you as an individual can do. Okay. So from tomorrow onwards, then we go into the issues related to the risks and ethics of the issues and things like that. Keep those things in mind. That think in terms of, because if we change the hat, if we get into the a slightly different angle into this, what you need to think about it is not what the model can do today, but how fast it is learning. So what it would be able to do tomorrow or day after, right? So that's another way of looking at it. All right, any questions? Especially if you're afraid of your future, of your sons and daughters' future in future, but the models are becoming intelligent very fast, no doubt about it. Come on, any questions? No? Yes?
Embeddings can be understood as group of tokens. Combination of tokens.
Okay. So we don't use the word combination or group there. So in a way, if you think about it, so I'm going to use the same words that I've used so far. We started with a single alphabet, right? Then we said the n-grams, which are nothing but the groupings of these things. We call it as sequence, right? And then we said that you end up with the words, which basically have some semantic meanings. So then I said two things here. These words are part of the embeddings, but then we realize that not only these are part of the word, part of the embedding, but these intermediate formations in a longer stream of words which make a sentence are also part of these embeddings. And the second thing I said that sometimes you see that things like these are also part of the embeddings. So nowadays the words that's being used is that tokens. That token could be a single word, or it could be a sentence, or it could be a fragment of a sentence. So the words that the two terms that we use is any token is something which is of interest, and a token, when it assigns a probability, becomes an embedding. Right? So what happens, like for example, let's say, and let me bring the RAG here. If you are, let's say, trying to build a system where you say that I am doing it for money laundering. How many of you know money laundering? I mean, the financial management guys. Can you define what money laundering is? Come on, the management guys.
Legal money to buy.
Sorry?
Like to show reflect black money as a white in a legal way.
That's you're answering the question why someone will launder the money. But what is money laundering?
Avoid from taxes.
Okay, that's why, but not still what is it? So, money laundering is basically when you are either trying to hide or obfuscate the source of the funding. That's the main thing. So, what happens is that when you have a transaction, there's a money coming in, there's money going out, right? The source of the money is important because depending on the source, you may have been already taxed or you want to be taxed here. So money laundering is trying to hide the source of money. That's just the definition, right? Have you heard this term called KYC? What does KYC mean? What does that mean? What does know your customer mean? Come on, if anybody's going in a banking job, finance guys, what is KYC? Know your customer means basically what that customer's source of incomes are normally. That's what KYC. So you might say that I do a business, or this customer does a business, this customer has a job, or whatever the case may be. How is that helping? Because the source of incomes are known. A lot of time when you do a transaction, you might see, I mean, I'm not sure here, but you have a lot of money suddenly coming in from this, which is not in line with your normal transaction. The bank will ask, what's the source of this money? Then you might say that, oh, I sold my ancestral land, that's where this money came from. That's all part of KYC. So, I'll tell you why I'm going into that direction. Money laundering is that when you're trying to hide or obfuscate the source of money, the way you do it, there is a term called layering. Have you heard of it? Right? What is layering? So when you cannot hide the source of the money, you try to obfuscate. And you do it by doing layering of transaction. So your aim is to transfer, let's say, $10,000 from here to here. You want to obfuscate, so you're not going to do this. You're going to say 2,000 here, 3,000 here, 1,000 here, 4,000 here. Then they all give it to someone else. They give it to someone else, and then eventually this person gets like 5 transactions of 2,000 each. What you're trying to do, you're trying to create, rather than one transaction, probably like 200 transactions of different amounts, different people, eventually getting it there. That's what we call layering, right? All right. Why I'm saying this, let's say you want to build a model whose job is to detect the money laundering transactions. Now, our language models don't know it, base models don't know it, or foundation models don't know anything about it. That's where this stuff comes in, and you say that I am embedding some tokens where layering has a different meaning, hide, obfuscate has a different meaning, source has a different meaning. So you're trying to teach the model specifics about your domain, which in this case is catching the money launderers. So KYC has a meaning, layering has a meaning, and then we go into more detail about these transactions, or which transactions are relevant, which transactions should it pay attention to. We'll talk about attention in a bit. So that's what is the retrieval augmented generation is. What we are trying to do, we are trying to inject some tokens in the model's semantic space or new embeddings with different probabilities, and then so that it picks those things much more frequent compared to what it would normally do. Make sense? All right. Any other question? Yes, no, maybe? No? All right. So we're going to go into the transformers and attention. As I said that, not too much mathematics, but get the intuition behind it. So even if you do not have a mathematics background, or even if you had a mathematics background, now you want to go into the management, understand how these things are functioning, because these are the most, I'll say, powerful architecture that has been used to build these large language models. All of them are using the deep neural network technology or deep neural network methodology, whichever way you want to call it, right? So far you guys are with me, right? From alphabet to words to tokens to embeddings, and each embedding having a probability, right? Let me bring one more thing that I used earlier, which was the context-free grammar or context-free language. We talked about it a little bit last week. Does anyone remember what the context-free language or context-free grammar was? Come on. Anyone? No? All right. The context-free grammar was that when a sentence meaning can be determined without any confusion, because the grammar does not have any dependence on the context. So if you write a Python program, right, or for that matter Java program, the language will not let you write something which is ambiguous. Not so in English. In English, the semantics of a word is determined by its context, right? Yeah, and that context could be grammar, could be anything related to that. Right? And the same thing is true with Hindi. Everybody understands Hindi, right? So if I write this, let me just give an example here. What does it mean? Right. So, I mean, I gave an example of English last week, but let me say I will try in Hindi. This could mean very different if you put a comma here or a comma here, right? So, even Hindi is not context-free. All of our languages are context-sensitive languages, which means the meaning of a word or a sentence will depend on the context in which it's being used, right? So let's see here. John picks up a magazine. We all understand. What does it mean? That there's a magazine somewhere and he picks it up. Susan works for a magazine. What does that mean? Let's replace the magazine, let's replace the John and Susan with some other names, right? I don't know, Mahesh picks up India Today, right? Now everybody knows that he's not picking up the building of India Today, he's picking up India Today latest version or whatever that is. Whatever, Shama works for India Today. Everybody knows that. Shama is not working for that paper, but that company India Today. So how you interpret magazine depends on the context, right? Bank. Bank is a bank where you deposit money. Bank is also a side of a river. That's also called bank. Banks of the river, banks of the Ganges River, right? Now, where the bank is a financial institution or where it's a land next to a river, how would a model figure out? That depends on context. And it's very simple. You and I can learn, or you and I have learned it over a period of time, that what the context is. If we are talking about deposits, withdrawal, check, money, then probably the bank is a financial institution bank. If we are talking about the Kumbh, Ganges, rivers, the Mela, whatever the case may be, then the bank is probably the land around the river or land around the water body. How would you make a model learns that the word's meaning depends on the context? Because if you want your model to be smart, they need to understand that words often have different meanings or different meanings based on the context. And clearly, we are not teaching the models these things, that the banks have two meaning, and in this setup, this meaning, in this setup. We want to enable the model to learn this itself. Okay? Now, little bit how we understood, because if you go back last week, I'm not going that far down, all our learning, I gave you an example of how does the baby learn, what the steps it takes, what the steps we do. So, now we're talking about English. We know that words have multiple meanings. So if you think about it, there are homonyms where a word has two different meanings, like bank. A lot of such examples exist. They're called homonyms. When there are two closely related meanings, they're called polysemy, just like magazine, in the sense that both are noun, but they have different connotations depending on the context. Now our goal here, not that we are doing it today, or the researchers were doing 10 years ago, is to see that can the model or LLM learn the same word or have the same word but with different vectors, or if you think about it in the terminology of the today, same token bank have two different embeddings depending on the context. That's what we are saying here. If the bank has two unrelated meanings, then in the LLM's meaning space that we introduced earlier, there cannot be one embedding representing the token bank, because it has two meanings. So we want somehow the model to figure out that the bank has two unrelated meanings. So depending on the context, it can possibly have more than one or maybe two embeddings, which means different vectors, different probabilities, different setup, right? That's what we are trying to see. How would a model do? How would a model do, in this case, the best way to represent the embeddings for a given token? Okay? This was a paper. Normally, when I teach the other courses, I always tell, especially the graduate students, who are about to go for research or something, you need to find 5, 6, maybe 8 papers that are fundamental in your area, right? And then make sure that you understand. In the case of large language model, this is what we do. How many of you are here who are doing the financial management or something like that? The MBAs? Come on, no one? I need to ask every single one of you what you're doing here. Okay, the reason I was asking is that anyone here has heard the Black-Scholes formula? Yes, no, maybe? All right, fine. Ignore that. Let's stand with the generative AI. Now, this was a paper published, majority of the Google's researchers, but there were a couple of University of Toronto people as well. The paper was called Attention is All You Need. If you want to do something about the large language models or transformer architecture, make sure that you read it. It's about 40 pages, I think, roughly. Pretty dense paper, but then easy to implement or easy to confirm that this works. So basically, what this did is it defined two things. It defined attention and it created an architecture called transformer, which is a specific kind of network architecture. Now keep in mind, what I said last week, when you are designing an intelligent system or AI system, you're figuring out weights and biases, and you're figuring out what kind of structure your network will look like. Earlier today, I gave you some examples of how researchers figure out that for simple functions, what kind of architecture is needed, not by designing it by hand, but figuring out how the model kind of structure itself. But still, they did that two hidden layers, one with 5 neurons, one with 3 neurons. They started with some lot of experimentation, which is what usually happens in the research. And then they came up with this architecture called transformer, which is the same as feed-forward network. Now, feed-forward network, we saw this in the sense that when you have multiple layers and each layer is sending or feeding its output to the next layer as input based on attention. So 2 things that we are going to focus for the next maybe 30-40 minutes about: attention and transformer. Not going into too much mathematics, not going into too much implementation detail. I left the slides here. I'm going to skip them because if somebody has an interest, you can go over them, understand them, but let's try to get the intuition. Okay? So let me give a very high level block diagram, if you may call it. Basically, if you think about it, I introduced the deep neural network having the layers. Now, this is a block. So literally what is going on is that we haven't yet defined attention. So I'll come back and then explain to you intuitively what's going on inside there. But if you think about it, there's a block called transformer. That block of the implementation inside is doing something called attention. Attention. And then what the attention is doing, and these transformer blocks are stacked over each other. So there are 2 transformer blocks here, which means that there are 2 inputs and 2 outputs. Can someone tell me, based on your understanding of what we have been talking about for last hour or so, and what I mentioned about the transformer and attention, what exactly is going on here? There's plenty of information on the slide itself to give you an idea. Tell me what exactly is going on here. Okay, don't go in those many words in the sense, just tell me like what exactly is based on this slide. Yeah, you may be right, but how did you get to that point? What makes you say so?
Analyzing the words by the various features like about the verb or nouns, and then it is correcting it to the sentences accordingly.
Right. So what is going on is that iteratively it is trying to give context to the words. So the initial sentence input was John wants his bank to cash the, say something else. The first transformer discovers that wants is a verb. Can it be something else? Yeah, wants is a noun also. Right? Your wants. What do you want? Your wants. Similarly, the cash is a noun also. So at the first iteration, this transformer is discovering that wants is actually used as verb here. Cash is also used as verb. Then the next transformer discovers that his is referring to John. Bank is a financial institution, not the river bank. Cash is a verb. So what is going on here? At each level, the transformer is discovering more and more about the tokens, the context of their tokens. Because the want could be different, the cash could be different, the bank could be different, his could be referring to whoever. This is what the transformers do. And how do they do it? They focus on attention. So let me ask you 2 questions here. Do you appreciate the fact that this is needed? Yes? Because English is not context free. It is context dependent or context aware language. So a good or an efficient or effective language model does require the knowledge of the context to appropriately decide which is the next common word to be used. You all agree with that? Right? So, the issue was that, and this was again about 10 years ago, the researchers all over the place, Google was obviously at the front of it, were trying to determine what architecture, what concept would let models figure out the context of every word to correctly determine how to form the next word. So, what they came up with a concept of attention. So really what is going on here, it says the transformer is the architecture, the two-step process to update the hidden state of each of the word, which is really the context. In the first step, it's called attention step, each word looks around and try to figure out its own context. So which word around a word has greater impact on its own meaning. So if you think about what I'm saying here, the bank trying to figure out is cash. So a cash gives a context to this bank that is not related to river. His, John, wants bank to do something to cash. That means it's a verb, not that it's a noun. So the whole idea was that every word, if it looks around itself, which is how you discover, right, whether it's an adjective or a verb or a noun, because you're looking at the sentence. Transformer is doing exactly the same thing. It has two phases. So first phase is attention phase, which is really every word is looking around and trying to find out what is the relevant context, and they share information with each other. Is that point clear? I'm going to ask this question, that how will they share information with each other? Obviously, if you are the humanities or the management background, you may not know it, but the science guys should really be able to figure out is that how do you share information with each other. Anyway, and then the second step is called feed-forward step. All the neural networks are feed-forward network. I just mentioned a couple of minutes ago that the output of one layer becomes the input to the next layer. That's what is feed-forward step. So each word looks around, tries to find what its context is, and share that information with each other. That's where they can figure out which is the best output. And then they move on to the next step, which then repeat the same attention step and then continues to feed it to the next layer. So usually you will find that transformer is an architecture which is doing an attention step, a feed forward step. By stacking a couple of these transformer one over the other, what was discovered that this kind of attention, this kind of context can be discovered by having a few transformer layers. So if you look at one of the modern large language model, you will see that there are up to 15, 20 different transformer layers introduced in there. So not only you have input layer, output layer, you have hidden layers, now you have transformer layers as well. What they're doing is that they're trying to construct context for each word. Make sense? So intuitively, that's what is going on. So we started with single neuron, hidden layer, softmax, then in between now we are introducing the transformer layers. And I'm saying that they are stacked because there are more than a few transformers that are discovering this. So our network is now looking like this. You have input, you have stacked transformer blocks which are trying to discover the meaning around each sentence, and then trying to come up with a much better understanding of what a network, what a sentence looks like, right? Now we can go and we will go a little bit into each of these things, because at the end of the day they are all neural networks, deep neural networks. There are layers, there are neurons, there are weights, there are biases, nothing else. There are mathematical probability functions as well. Not go into too much math, but this is what we're going to do next. All right, so something is missing from here, but that's fine. Let's move on. So it's just a quick recap. Static embeddings, which we saw earlier, example of only two things, single alphabet and a combination of two, which are static embedding. Nothing is changing. They are static, the probabilities are known, and then you figure out what exactly. The problem with such is that you take another example, it. How does it know what is it referring to? Is it referring to chicken or is it referring to road? You know it, the road doesn't get tired, it's only the chicken who can get tired, so it must be referring to chicken, but a model doesn't know it. How would the computer know it? Right? That's what is basically the context is about to do. If you have static embedding, there is no way you can figure out what is it referring to, because you know it, that's why it's referring to. Okay, all right, so let's continue to build with this intuition here. Meaning of a word can be different. It says should be different, but think of it this way, can be different in different contexts. I mean, really speaking, the should is fine, because if it is not different, they're not different contexts, they're same context then. The contextual embedding is that, and I mentioned this already earlier, that if you have a different meaning in some context, the word will have a different vector or a different embedding. Right? How do you compute these embedding? That's what is called attention. Okay? Let's look at the example of an attention. And again, I have separated out the intuition from the mathematics. So let's see if everybody gets the attention part intuitively. So what's going on? We have multiple layers, right? At this layer, it comes across the chicken, the road, and then it says it. At the next layer, what it is trying to do is that it can only refer to either road or a chicken. It can also refer to the in some cases. So what is going on is that the attention phase is limiting the scope of what it should be considering. We haven't gone that far when you see that the tired is referring to it, and then from its basic understanding says the tired is never associated with road in my previous learning, so the tired must be associated with chicken, which means that it must be referring to the chicken. That's what is happening in each stage. So what the attention is doing, attention is saying that, and if you go by two other slides earlier, each word is looking around and seeing that which one of these words around me have a higher impact on me. How? Based on the prior learning. Okay? If you had two vectors and try to find the impact of the component of each of those vectors, how would you do that? Dot product, right? If you create a dot product of two vectors, you find the resultant vector. Really speaking, if you think intuitively at a very simpler level, what we are doing, we said each of these tokens are also vectors. That's what the embeddings are, sequence of numbers. When you multiply each of these things to the other ones, if the embeddings were discovered correctly, that's how it's calculating. So if you think about it, each vector in a way is a matrix. It's calculating dot product. So by simply creating dot product of a word with every other word surrounding it, the model discovers, based on the prior learning, which one of these words have higher weightage. Once you do it in multiple layers, the expectation is that it will figure out the context correctly, and it does. So the dot product, what it does is that if you're multiplying two vectors of the same dimensions, the wherever there is a higher value, it will basically get enhanced. The lower values will get further lower. That's what the dot product does. The resultant vector will have that kind of behavior, right? All right, make sense? So what is happening here is this. It takes the surrounding tokens at the previous layer, will do the dot product, and then basically creates a weighted sum of vectors, and then they become input into the next layer. By iterating this process a few times, what was observed that the network or the model is finding out the context almost correctly every time. Right? Basic simple math. Do you get it intuitively as to what is going on there? Yeah? So I'm going to bring in the first mathematical slide, but it's exactly same thing what I said. I'll be happy to go to and fro to explain what was going on here. So x1, x2, xi are the token embedding. Each x represents a word. The word is represented by a set of numbers that we have talked about. What we are trying to do is a weighted sum of every single of these vectors weighted by their similarity to xi. So let's say we are trying to find out the attention of xi. Which one of these are going to have more impact on it? You calculate a score by doing a dot product of xi with every xj. Let it go through the softmax because you want probabilities that which one of these have higher probabilities of impact or attention on xi. You get up with a number, and then basically higher the number, higher the probability of the context that it might have. So same thing that I talked about earlier, represented mathematically here. Does it make sense? So if we started with here, this one, now it looks like this. So you say that xi, we are trying to find out it. What does it refer to? Then you basically go and then calculate the xi's vector multiplied with every other vector. Now the assumption is that that vector, which is the embedding, which is the weightages find in some higher dimensional space, will have values which when multiply would say it could either refer to road or to chicken. And in the next stage it will say tired. Tired is most likely going to go with chicken, not with road, so it is going to be associated with the chicken. So this one is represented here mathematically. Make sense? Okay. So how is it done? Little bit more before we make a stop in about 9 minutes. So the way it's going on, and again a very high level idea. So xi, x4, instead of using them directly, they are being represented in 3 different matrices. Query is the element being compared. Key is every preceding input that is being compared, and the value is the output that is coming in. So if you think about it, xi is a key, x1 to x7 is the query, and then the value is coming is the output, which in the next one will become input. So 3 things that we are computing: query, key, and value. Query is the current element being compared. Key is everything prior to that. Value is the output. The value in this phase will become a key in the next phase, and the query word will keep moving one word, one token at a time. Make sense? If any of you want to implement the attention paper, what you would end up doing is writing some matrix calculations using these matrices: query, key, and value. And in every iteration, the value from the prior iteration will become key in the next iteration, and the query will move one token at a time. Sorry? Any questions? Yeah.
How does the model generate new tokens while a model has attention on previous layers key queries and key values? Then
Okay.
how does
So let me stop you right there and see if you can rephrase it. Model is not generating any token. Tokens are all coming as part of input. What the model in this phase is doing is that finding out which token has higher impact on the other tokens. So if you want to rephrase your question, then it's not generating any new token.
Model takes tokens from previous layers.
No. So the layers are all same. So tokens are all same. What is going on is that it's looking at each of these tokens one at a time and then trying to calculate which preceding token had higher impact on the current token. So in this example, this is query, xi is query, everything here is key. The output becomes value, the value of this layer becomes key to the next layer. So what is your question now?
Question is, how does the model generate new tokens?
No. So the okay, hold on. Are you saying the new token means the next token here?
Model takes tokens from previous layers.
Yes.
How does it generate new tokens?
No. Okay. So there are two separate things that you're talking about, if I understand correctly. So in the generative AI, we are always saying that it's always generating the new token, right? Now, what I am saying today, to generate this new token, it has to know which token has a higher impact on this new token. This process is simply discovering which one of the prior tokens have a higher impact on whatever is the next previous token to the next. Before generating, it is trying to figure this out. Does that make it clear? Okay, so let's say this one more time. Anybody else actually has a question or thing? I'm just going to go one more time to explain the entire process, but is there any other question? Okay. Yeah.
Weighted sum we are taking of the query with the keys.
Yes.
So at each layer, after going to each layer, we will have the value of that alpha.
Mm-hmm.
So that alpha will be for the entire layer or for each combination of query and key.
Each combination of query and key, exactly. Actually, each combination, each query. So what your goal is, so let me just combine the two things, and that's where the confusion was, right? See, the goal of the entire LLM is to predict the next token based on what it has seen so far, right? So the end goal is this, to predict the next token. But how do you predict the next token? By looking at this, because this is not context free, right? So if it has a token called it, now the model needs to figure out first, what does it refer to, right? In this example, was it referring to road or chicken? To do that, even before you can predict the next token, you need to apply this transformer logic. And that's where I'm explaining, without even going to how the next one will come, what is it referring to? So this layer, and the next one is determining that the it is referring to chicken, not to the road. Is that clear? Right? And your point was that the weighted sum is being calculated for every one of these tokens. It didn't matter for cross, the, because, but it mattered for it, because it was not clear that whether it is referring to this noun or the other noun. Make sense? No? Okay.
So actually my question is, for entire layer, we are taking this weighted sum of alphas, or we are computing alphas for each query and key combination and then finding out which makes more sense.
For each key query combination.
Okay.
Right? And then figuring out, see, here's the thing. For this one, it makes no difference because this is unambiguous. This is unambiguous. This is unambiguous. This process makes sense only when you come across this. You're computing it for everything, but it makes meaningful for this only. So we are computing for everything, but it's only meaningful in this case.
So the meaningful combination only will go to the next layer.
Everything will go to the next layer. Everything will go to the next layer. But what will happen is that you will see that in each subsequent stage, this will be a higher value, everything will start going down. So it will emerge as that this one is the one which requires more attention. Does that make sense? Okay. So then what is going on is that we have query, key, and value, and then in a way, this is what is going on. The word like it, so it will have an attention head. So what will happen is that each layer will have attention head, which means that many times this process is repeating and it's figuring out that what exactly is it doing. One of the attention head will end up matching pronoun with noun, which is the example we saw just now. Other one might be doing the resolving the meaning of homonyms like bank, which is the example I'm not showing here, but I said that once it figures out that it can only belong to either road or chicken, then it will figure out that tired. The tired has to be associated with either road or chicken, and then it will determine that a road cannot be tired, it must be chicken that's tired. So these are all attention heads, or the pieces of the information that it is trying to figure out that which of the meaning of a word is relevant in the current context. Another attention head might be trying to link two word phrases, like Joe and Biden are representing one single concept, Joe Biden. So there might be a lot of different attention heads which might be required for one single sentence, right? Okay, we take one more slide and then we'll stop. Generally speaking, GPT-3, and this is old, a few months old, not GPT-3o, had 96 layers which were doing the transformer, 96 attention heads each. So really speaking, every time it was predicting a new word, there were 9,200 odd attention operations being carried out. So it's a whole lot of calculation before it predicts one single word here. 96 heads, 96 layers in 96 transformer layers basically that it's doing. Yeah.
Sentence you gave, that sentence related to the LLM model, or it generated itself, the whole sentence?
Okay, so it could be both, because if you think about it, in the unsupervised learning model, every input is learning as well as generation. So it doesn't matter whether this sentence was fed to it to begin with, or it generated all of it until this point. This was an example to show that how does it determine what does it belong to. So the basic functioning of transformer layer is independent of where the sentence came from. However, when you are doing the multiplication, those multiplications are happening based on the probability that is already learned, right? So it doesn't matter whether this was generated or this was given as an input. Okay, the attention head is basically, so in this case, in this example, it's trying to determine the pronoun and trying to figure out which noun it is referring to. There are different type of attention heads, because this is again something that we know our language, the peculiarities of our language. So one is this one, which was matching pronouns with nouns. The second bullet point says that trying to resolving the meaning of homonyms, whether the bank is a financial institution or bank is the side of a river or a water body. So one attention head is simply trying to do that. The other one is trying to figure out that if there are two words which are added together, right? Like Joe Biden. So it's telling the model, saying that don't think Joe is separate and Biden is separate. They're together a single semantic unit. Any other question? Sorry? Oh, self-attention is basically the same thing that we are trying to say here. Every word, when it becomes a query, it is trying to find the attention on itself. That's what we are saying is that the self-attention layer. Every word at one point or the other will calculate a self-attention in the sense that what is the impact of the words surrounding it on itself. Okay? Now, one thing which, this is a very simplistic model that I have shown here, right? So the thing that I have not mentioned here in this example, this is only showing the words or tokens that is seen so far. In one version, it might be looking at the words on the other side also. In some cases, it may not be in the every pass, but in some layers, it's looking at both sides. Okay? All right. Yeah, I think we should stop at this point and then we come back and continue a little bit more on attention and transformer. We'll skip the math portion. I'll leave it for if some of you have interest in them, then you can continue on those. Okay? All right, let's break a little bit. And I promise it'll go much more softer concepts rather than the hard math going forward. Yeah, should stop a little bit. So when do we meet here?
15 minutes.
15 minutes?